Alright, so you've had a few minutes to work through this. Let's go ahead and see how you did, okay? Now, the image that you were given for this one is we were trying to revolve this area between the curves, or the region bounded by the graphs around the x-axis. You could see where the intersections were, but how would you find those on your own? Set them equal to each other, okay? Now this actually brings up a good point. If I set these equal to each other to find these 2 points, okay, I've got square root of x equals x squared, and I would need to square it on both sides to get something that I could solve, okay? And then if I subtract x from both sides, I get x to the fourth minus x. I factor out an x and I have an x cubed minus 1. And all of you recognize that you can keep factoring, right? You can keep factoring using what? Okay, it's the difference of cubes. And we had that acronym SOAP to help us remember the signs. Same, opposite, always positive. So this x is still here. I put the cube roots in the first set of parentheses, and I use the same sign there. And then in the second set of parentheses is a trinomial, and the sign here is going to be opposite, and then this last sign is always going to be positive. Okay? And then you simply square the first term to get the first term in here. You square the second term to get the last term in here. And you multiply the terms together to get the middle term. Okay? So 1 times x is just x. Okay? So square, square, product. Okay? Now, this last trinomial here, if you tried to solve it, we would get no real roots. No real number roots. So we see here that the only intersection points are x equals 0 and 1. You are not going to always be given this information. You won't always be given a diagram, okay? Now, you could have also figured this out logically. Just think, what number could I square and square root and get the same answer? 0 and 1. But this is how you would have to figure it out if you couldn't think of it. Okay? All right, so what formula did you guys set up? So I want to share what they had?
I times the integral from 0 to 1 of x squared minus, or no, just x minus 4x. X to the fourth, oh my goodness.
Okay, so you did the square root of x and you squared it, so you got an x. And then you did x squared and squared that, and you got x to the fourth. And that's correct, all right? Remember, you take the upper function. The upper function in this case was that square root function. Okay, so here is square root of x. And this lower function here was the portion of the x squared function. Okay? Yes?
Can I ask you something? Did we do something like not squaring them separately or together?
No, we actually have to square them separately before we subtract.
Yeah, I know. And they told me that I should do that here. But did we do something like that before for another kind of question?
You know what? We weren't squaring it, but when we found the area between two curves, just the area, not volume, we could do the area under the first one minus the area under the second as two separate integrals, or you could do the function minus the other function and just take one integral. That might be what you're thinking of. Okay. Here, though, we do have to be careful to square first, so it's x minus x to the fourth, and then we'll subtract. Okay. So we take the integral x squared over 2 minus x to the fifth over 5. We have to evaluate that from 0 to 1. And what'd you guys end up with here?
3 pi over
3 pi over 10?
Yeah.
So what the rest of you guys got? Okay. All right, 3 pi over 10. This doesn't give us units of measure, but we know they're cubic units of some sort. Okay? Now, what I want to actually do to take this one step further is, and I think this would be helpful for everyone to see one more example of this, is what if I didn't want to revolve it around the line x equals 0, the x-axis, or y equals 0, the x-axis? What if I wanted to revolve it around a different horizontal line? We'll stick with horizontal here. Let's say I wanted to do this around y equals, what should we do it?
-1.
-1? Okay. So y equals -1. So I'm actually going to revolve this around, here's -1 down here. Yeah? This is not part of the original problem. I'm just doing this because I know we did 1 or 2 of these, but these can be tricky, so I just want to make sure that we get a little more experience. Okay, so what I'm doing here is I'm actually going to have a hole inside of this. It's going to be like, it's going to probably look kind of like a tulip that you cut the middle out of or something like that by the time we're done here. It's got this big hole in the inside with a radius of 1 unit. Okay, but it's going to have this kind of, you know, leaf shape as its wall all the way around. All right, so this is going to look pretty cool. What do we need to do in order to work with this? Huh? Yeah, we're going to move everything up 1 unit. If you're not revolving around the x-axis, make it revolve around the x-axis. Okay? So,
When you move it down?
well, you pick -1, right? So to get that line that we're revolving around to be the x-axis, I've got to move that line up, and in order to keep the same shape, I've got to move the entire thing up. All right? Yes?
Can we just say, like, we're subtracting -1 from each?
You are subtracting a -1 from everything, so you have, that's adding 1. Yeah, you could think of it that way. Okay? So, in order to do this, if you think about your transformation here, if I'm going to shift something up 1 unit, I'm going to add 1 to the y, all right? Or to the function, okay? To f of x. So y equals 0. Now I'm revolving it around the x-axis, but I need to add that to my other functions as well. Y equals the square root of x plus 1, and y equals x squared plus 1. Okay? Now I've shifted everything up, so essentially what I have now is, now this is my axis of rotation again, or revolution. Now I have them intersecting still at 0 and 1 on the x-axis, but my y-coordinate has pushed up until it's like this, okay? So I've got this up here because I've moved everything up, okay? Now, with these, you do have to be careful just to double check and make sure that the upper function is still upper and the lower function is still lower. Earlier in the other class period, we rotated it around the line y equals 1 instead of -1, so we shifted it down, and that actually reversed which one was further away from the x-axis and which one was closer. So we had to reverse the subtraction up there. This one, we don't have to do that with.
How would you know?
Yeah.
Look at it.
But wait, so what was the
Sorry.
you were transforming it down?
Yeah, this morning we revolved it around the line y equals 1, so we had to shift everything down. And when I did that, this was the square root of x minus the 1. And this was x squared minus the 1. And when you go below you can't think of like upper and lower like you typically would. You got to think which one is further from the axis and which one is closer to the axis. So in this case, because it ended up moving below the axis of symmetry, or the x-axis, the x squared minus 1 would have to come first in the subtraction, and then we subtracted the square root of x minus 1. You guys actually inadvertently picked an easier one to handle with. Yes?
Why not just find the absolute value?
Find the absolute value? You can. If you accidentally mess it up, if you accidentally put them backwards and you get a negative volume, yeah, take the absolute value and fix it.
That's
So
why
can't
I
you
always
just
find
Okay.
the absolute value.
What?
Can you always just like?
You can. You can.
Oh, okay.
You kind of show us you know a little bit more what you're doing if you set it up right in the first place. But it's an easy fix. It's an easy fix. All right. So we've got our functions now. So now our volume is going to be pi times the integral from 0 to 1 still. We haven't moved it horizontally at all, so that's the same. Of the upper function. So that upper function is square root of x plus 1 squared minus the lower function, x squared plus 1 squared dx. Be careful to FOIL this time. This time it's a little bit more complex because we're foiling, we're going to have more terms. But still, at this point, it's not too bad of a process. So let's just wrap this one up. Simplify what's in the integral. We've got x plus 2 root x plus 1 minus x to the fourth minus 2x squared minus 1. Okay, you all know how to FOIL. The plus 1 and minus 1 cancel each other out. That's kind of nice. But there are no like terms, so I can go ahead and just integrate at this point. It's pi, and I've got an x squared over 2. I've got an x to the 3 halves times 2/3, and I already had a 2 there, so it's going to be 4/3. Minus x to the 5th over 5 minus 2x cubed over 3. And I got to evaluate that from 0 to 1. Thankfully we have nice easy numbers to work with, okay? The 0 just comes out to 0, so that's nice. This whole thing is going to be pi times a half plus 4/3 minus 1/5 minus 2/3. Okay? So our common denominator here is going to be 30. 15 plus 40 is 55, minus 6 is 49, minus 20 is 29. So this is going to be 29/30ths pi cubic units. Okay? Yeah.
So the intersection points always stay the same?
If you're, basically, yeah, because if you're revolving around a horizontal line, you would only have to move it up or down, so your x's won't change. If you were revolving it around a vertical line, you would just be moving it left and right, but then your bounds would be y coordinates, and those would not change if you're just moving the functions left or right. So either way, your boundaries should not change. Okay, great question. All right. Yeah.
Just like that part, parentheses around the
Okay, with our last two here, I want to just address two other possible issues that you might run into with this number 4 here, example number 4. We're integrating with respect to y, but, okay, this is what you got to be careful about, all right? But notice here, I'm revolving around a vertical line, so I've got to integrate with respect to y. First of all, our function wasn't given in terms of y, it was given in terms of x, so we got to do something with that. Secondly, if we look at this as the function further away and the function closer to the axis, notice we are actually going to need to break this up into two separate pieces. Okay? Two separate pieces. You can see here, this equation, y equals x squared plus 1, hits us at y equals 1. If I'm integrating with respect to y, I can't take an integral from 0 up to 2 when my function is not defined below 1 or between 0 and 1. Okay? So I have to break this up, and you can see how they've done this here. They broke it up into two separate integrals. And basically what we're going to be doing here, you can see here on the 3D image, okay? We have this just plain old cylinder on the bottom. Okay? That's kind of nice. We don't even have to do an integral for that, right? We know the volume of a cylinder. Volume equals pi r squared h. What's the radius here?
2, 1, so
1. 1. What's the height here?
2. No, y.
Of that bottom part, it's just 1, right? So yeah, right here, the height equals 1, and the radius equals 1. So 1 squared times 1 is 1. So that bottom is just pi for the volume. Okay? Don't try to integrate from 0 to 2 with a function that's not defined for that whole value. Okay? For all those values. So, let's deal with that top half. This top half is just, it looks like a regular cylinder on the outside, but it has this bowl shape cut out of the top of it. Okay? So for this, we're going to be integrating with respect to y. Now, what are the bounds going to be for this integral?
1, 2.
From 1 to 2. Y equals 1 to 2. Okay? What is the outer function or the further function in this case?
2. I mean, the x squared.
X equals
X 1. Yeah.
X equals 1. It's this vertical line here. Okay? And yeah, that's not a function, but we're just kind of like turning our heads here a little bit. So the one that is further away from the axis of revolution is that x equals 1. So when we set this up, it's going to be 1 squared minus the other part squared. Okay? So here's where we got to do a little bit of other work. Okay? We have this. Huh? Yeah, they gave it to us. But that's where it came from. Okay? Y equals this. So we just solve it. Okay? Y minus 1 has to equal x squared. I square root both sides, and the x, or the inner radius, if you remember, that inner radius is the square root of y minus 1. Okay? That's that inner radius. So, that's what's going to go right here.
Mr. Rosen,
Yes?
so like the two functions are both in terms of x? Like how do you
Yes.
know when it is or not?
It's got to be, well, when you're integrating with respect to y, you have to be integrating functions that are in terms of y.
Okay.
So it has to be x equals something.
So like here it doesn't say integrate, like how would we know?
Well, we're revolving the region about the y-axis. That's the key right there. If you're revolving it around a vertical line, you've got to integrate with respect to y.
Okay.
When we revolved around a horizontal line, we were integrating with respect to x. Yeah.
Is it pi times that integral?
Yeah, it is pi times that integral. So our volume for the top is pi times that. Okay? So this is kind of nice. The square undoes the square root. It's pi times the integral from 1 to 2 of 1 minus y plus 1. Don't forget to distribute the negative. So that's just a 2 minus y. Okay? So, at this point, it's really easy. We're just taking the integral 2y minus y squared over 2 from 1 to 2. Okay? So it's pi times, I have 4 minus 4 over 2 minus parentheses 1 minus 1/2. So I have, or sorry, not 1 minus 1/2, 2 minus 1/2. Okay? So I have 4 minus 2, which is 0, minus a negative 1/2. So that's plus 1/2 pi. 4 minus 2, minus 2, so that's all 0, minus a negative 1/2. Okay? So that's just the top. And here, this was the volume of the bottom. So, the volume is simply pi plus half a pi. So 3/2 pi cubic units. Okay?
So the volume of the top, the 1/2 pi, that's the, like, not the cone, right? That's like the around.
Yeah, if you were to look at this from the outside, it looks like a total solid cylinder. But if you look from above, the top half of it is like a bowl.
So
And then the bottom is solid.
the reason why, like, one of the functions is y equals 1, or I mean x equals 1, is because the bottom, is that what it is?
Yeah, that's actually the outside. The outside is just a plain old cylinder
Okay.
with a radius of 1.
Okay, so is it like going like,
Yeah, it's going around like this.
okay, I just have a hard time like.
Yeah, it's hard to see 3D on paper or on a wall. So,
So you just added the two together.
correct. Correct. All right, last one here. I'm going to cut off the bottom, and don't look if you have the notes in front of you. All right. A manufacturer drills a hole through the center of a metal sphere with a radius of 5 inches, as shown in the picture. Okay. The hole has a radius of 3 inches. What's the volume of the resulting metal ring? Now, we have a sphere. How do you make a sphere using solids of revolution?
Would you just do like a semicircle?
Yeah, we would have to get a semicircle and spin it around, right? So we do a semicircle. Now, to get a semicircle, you have to have the equation of a circle. What's the equation of a circle? Well, that's the area of a circle.
It's like x squared, so it's the h and the k thing, right?
Oh,
X
it's squared.
minus
It's squared.
h.
It's x minus h squared plus x minus k squared
Y minus
over
k.
r.
Equals
R squared.
equals r squared. Okay.
Everyone's
So-
so excited because we actually know this.
Yeah, no, it's good. That's good memory. So here's the deal. They didn't tell us where this thing is, so let's put the center right at the origin. So we don't have to worry about h and k. That's a nice thing. So our equation that we're going to start working with is simply the equation of the circle. X squared plus y squared equals r squared. And since we were told that the radius was 5 inches, we know this equals 25. Okay? Now, and I'm doing this because you're not always going to be given this diagram over here on the left, all right? If that's 25, x squared plus y squared equals 25, I need a function to work with here, okay? I need a function to work with. So I'm going to solve this for y, and that's going to be y equals 25 minus x squared square rooted. I don't need to worry about plus or minus, because when I spin it around the x-axis, I'll get both of them anyways. Okay? Alright, so that's how, over here, they get that this outer radius is going to be the square root of 25 minus x squared. Now, if I want the inner radius, or that hole that I'm cutting out, to have a constant radius of 3 inches, then I could just use the line y equals 3 as my lower function. And that's why you see that here. Y equals 3 is that horizontal line. Okay? Now, here's the challenge with this one. How am I going to figure out the boundaries of my integral?
Would just be the radius. 5 to 2.
You
No,
can't
no.
find-
You can do the integral of 1 minus the integral of the other.
You can't set the integral to.
Yeah, but what are the boundaries that I should use?
5 and negative 5.
Can't you set
5
the
and
integral?
0. What would be the diameter?
Check this out. Look, if I tried to integrate from negative 5 to 5,
That would equal 0.
I'd be getting this stuff over here that I don't want, right? But I can't do this because that's where they cross, and now it'd be backwards. So what do I have to figure out? I think, Rebecca, you were kind of on the trail of this.
Don't you just set them equal to each other?
Okay, find the intersection. Where does this hit y equals 3? And actually a little triangle might help. If y equals 3 and I know the radius is 5, what's this side?
4.
It's 4. It's a 3, 4, 5 right triangle. Or I could use the Pythagorean theorem. Or I could set this whole thing equal to 3 and actually solve it algebraically. Okay? So 25 minus x squared equals 9. And that means 16 equals x squared. So x is 4. Or negative 4. Which you could have figured out logically, but either way, here algebraically you get both sides. Okay? So now I know how to set my integral up. My volume is going to be pi times the integral from negative 4 to 4 of, oh, I drew that too high. Let me bring that down. The volume is pi times the integral from negative 4 to 4 of the outer radius squared, so that's square root of 25 minus x squared, squared, minus the inner radius, 3, squared. Now, before we integrate, how could I make my life easier?
Simplify.
Well, isn't square root, isn't it the, I can't think of the word. They cancel out each other, right?
You just do the integral of 2.
Yeah. Simplify.
Well, we are going to simplify some stuff out, but wait, what are you saying?
2 integral, like, for
Or
each.
2 times the, oh!
I could do 2 different integrals, but wait, what were you saying?
2 times from 0 to 4.
Ah, hey, isn't this a sphere?
Yeah, so
And it's perfectly symmetrical? So, I could make life a little bit easier if I made it 2 pi, and I just did the integral from 0 to 4. And the reason why that'll be easier is when I go to do my fundamental theorem of calculus, I get to plug in a 0, and that's always a good thing. Okay? When we get to plug in 0 instead of like a negative 4, that's a lot easier. Okay? So, now I've got 25 minus x squared minus 9 dx. So this is 2 pi. That's going to be a negative x cubed over 3. And that's a 25 minus 9 is 16. So that's going to be a plus 16x.
why is it subtract? Why is it 25 minus x squared?
Up here, when I was solving for y, I had to subtract x squared from both sides.
But when you FOIL it, isn't it 25 plus x squared?
Well, we're not foiling. It's square root squared, so it's just gone. Okay? So now, like I said, when we get to plug in 0, that's that's nice, because this thing just equals 0. So I just have to plug in 4. 2 pi times a negative 4 cubed is 64 over 3, plus 16 times 4 is 64. So I have 64 minus 21 and a third, which is going to be 42 and 2/3. Okay, I multiply that by the 2. 42 and 2/3 is 85 and a third, which I know all of you can figure out. Okay, this one we do have units of measure for, so we should put inches cubed, or write out cubic inches. Okay, that's the volume of this metal ring. Okay, so now if we know the cost of that metal, we can figure out how much it's going to cost in materials to make this thing. Okay, so, or if we were buying the balls pre-made, we know how much scrap we're going to get out of it, and then we can melt it down and make more. Okay, so